When solving limiting reactant problems, it is important to remember the key things to look for to identify we're dealing with the limiting reactant problem in the first place. Other than the first part of the question asking us what is a limiting reactant, the key thing we want to look for is the fact that I'm given the amount or the grams of how much of both reactants that I'm starting with. We aren't given one of the reactants in excess like we have seen in the previous video. So when I solve these problems, I'm still going to create a BCA table. And the nice thing about a BCA table is that once you fill this table in, you're going to have all the answers to all the questions you could possibly be asked about these problems. Remember that the limiting reactant is what reactant we run out of, and the excess reactant is what we have left over. So I'm going to start by filling in my table in the same ways like we did on the last video. I always have 0 of my product before the reaction has started. I then can go and fill in my change. I have negative of my reactants and positive of my products. I use the coefficients in the balanced chemical equation to fill in those x's. So here this would be negative 2x. This is a 1, so this would be just negative x. This is a 2, so this would be plus 2x. And then this is a 1, so that would just be plus x. I then can take the masses that I'm given in the problem and plug those into my table. But it's important to remember that the only numbers you can put in the table are moles. So I need to take 24.5 grams of sodium chloride, and I'm going to convert that to moles, and 41.3 grams of fluorine, and I'm going to convert that to moles as well. So I need to find the molar mass of each of those compounds. The molar mass of NaCl would be 22.99 plus 35.45 to get a total of 58.44. And then I can do 24.5 divided by 58.44. So I know that I have 0.419 moles of NaCl. The mass of fluorine is 19, so if I have 2 of them, this is just going to be 38 grams. So I can do 41.3 divided by 38, and that's going to give me 1.09 moles of F2. Now that I have these values in moles, I can plug them into my table. So I'm starting with 0.419 moles of NaCl and 1.09 moles of F2. The next thing we have to figure out is which one of these goes to 0. I cannot assume that both of these go to 0. One thing you can do is you can look here and see that I'm starting with less NaCl, so that might be a clue you're going to run out of NaCl first. I can also see the change. This is changing by a factor of 2x, whereas this is changing by only a factor of x. So not only do I have less NaCl to start with, I'm also losing it or using it twice as fast as the F2. So I can make an educated guess that I'm going to run out of NaCl first. Now, in order to check to make sure you pick the correct limiting reactant, we're going to solve this equation, 0.419 minus 2x equals 0. We're going to solve this for x. I can divide both sides by 2. And I can get that x equals 0.2095. Now, in order to check, we're going to plug our x back in, 0.2095, and we're going to see what number we get here. As long as we get a positive number here, we know that we picked the correct limiting reactant. And 1.09 minus 0.2095 equals 0.8805. So because this is a positive number, I know I picked the correct limiting reactant. Had this number been a negative number, that means that this would have been the limiting reactant and you would have had to go on and resolve for x. So now that I know my x value, I can plug it in on the product side. So this would just be 0.2095, and this is going to be 0 plus 2 times 0.2095. which is 0.419. Now I have my entire table filled in. I can go back to this first question, what is a limiting reactant? Remember, the limiting reactant is the reactant that is limiting how much product we can make. Or you can think of it as the reactant that you run out of. Because NaCl goes to 0, I know that NaCl is going to be my limiting reactant. The next question is, how many grams of excess reactant are left over? Well, I know that F2 is my excess reactant, and I know that that is the number of moles that's left over. So all I need to do to find this is I can take 0.8805 moles of F2, and all I have to do is convert that to grams of F2 to find the mass. So I know in 1 mole of F2, I can use this molar mass I found earlier of 38 grams. So I can just do 0.8805 times 38, and that would give me 33.46 grams of F2 are left over. So I started with 41.3 grams, and I have 33.46 grams left over. And then the last question, C, how many grams of chlorine gas are produced? Well, this is chlorine gas, and these are the moles of chlorine gas that are produced. And so to convert to grams, all I have to do is multiply by the molar mass of Cl2, which would be 70.90. So 0.2095 times 70.90, this would give me, and my answer to C would be 14.85 grams of Cl2. So here you can see that once you fill in your BCA table entirely, you are going to be able to present or find the answer to any stoichiometry question you could be asked. So in our next example, we'll look at the problem. An 84.1 gram sample of phosphorus will react with 85 grams of oxygen gas according to the reaction below. So this is a stoichiometry question because we're asked for the limiting reactant. And I know this is also a limiting reactant problem because I'm starting with 2 numbers or 2 values of the reactants. This means I'm going to have to figure out which reactant I run out of first. As with all stoichiometry and limiting reactant problems, we're going to start with a BCA table. Remember, it's important to make sure you have a space for every single reactant in the problem and product. Again, I'm always going to start with 0 of my reactant before the reaction has started. I'm going to move this line over just a little bit. Then I can fill in the change. So this would be negative 4x, negative because it's a reactant, 4 because the coefficient is a 4. This coefficient is a 5, so this would be negative 5x. And then for my products, this would be plus 2x. I can then take the numbers from the problem and plug them into the table. Again, it's important to remember that you cannot put grams in the table, so you're going to have to convert these numbers to moles. So 84.1 grams of phosphorus and 85.0 grams of O2. All I have to do is divide by the molar mass of both of these substances to find the number of moles. The molar mass of phosphorus is 30.97. And the molar mass of O2 would be 2 oxygens, which is 32. So 84.1 divided by 30.97 would give me 2.72 moles. And 85 divided by 32 would give me 2.66 moles. So now that I have the moles of my phosphorus and oxygen, I can plug those into my table. So 2.72 moles and 2.66 moles. Again, you are going to have to figure out which reactant you run out of first. I can look here and see that I have a slightly less O2 than I do phosphorus, and also I'm using up the oxygen a lot quicker than the phosphorus. I'm using 5 oxygens but only 4 phosphoruses. So we can make an educated guess that oxygen will run out first, and that would make oxygen the limiting reactant. Again, in order to check, I'm going to solve this equation. 2.6 minus 5x equals 0. I'm going to solve it for x. Can divide both sides by 5 to get that x equals 0.532. And remember, to check this, you plug your x back in to the other reactant to see if you get a positive answer here. So 2.72 minus 4 times 0.532 gives me 0.592. And because this is a positive number, that tells me that I chose the correct limiting reactant of O2. So what is the limiting reactant? I know the limiting reactant is O2 because that's the reactant that went to 0. I'm going to finish my table. I'm going to plug in my X, 0.532, to figure out that I had, so this would just be 0.532 times 2 to get 1.064. That's how many moles of P2O5 were produced. So when I go and look at answering B, it says how many grams of excess reactant are left over. Well, I know P is the excess reactant, and I know that 0.592 moles of P were left over. So all I have to do is take that number of moles, multiply by the molar mass of phosphorus to get the number of grams of excess reactant left over. So 0.592 times 30.97 equals 18.33 grams of phosphorus. Let me rewrite that really quick. Grams of phosphorus. So I know that 18.33 grams of phosphorus, my excess reactant, were left over. The last question, how many grams of P2O5 can be produced? I look at my table. After the reaction, I have 1.064 moles of P2O5. So all I have to do is multiply that by the molar mass of P2O5 to get how many grams I produced. 2 phosphoruses, so 30.97 is phosphorus, I'd multiply that by 2, plus the mass of 5 oxygen. Oxygen is 16, so 16 times 5. And that gives me a mass of 141.94. So I can just multiply that by 1.064, and that will tell me that I had 151.02 grams of P2O5 after the reaction was completed. In our last example, we'll look at the problem. A 5.75 gram sample of silicon dioxide reacts with 5.5 grams of sodium hydroxide according to the chemical reaction shown below. Again, this is a limiting reactant question because not only does it ask me to find the limiting reactant, but I see that I'm given the mass of both reactants. So I'm going to start by filling in my BCA table, making sure that I draw a box under each reactant and each product present. It's important to remember that I'm going to start with 0 of my reactant or products before the reaction is started. This makes sense, or hopefully it makes sense, because before the reaction is started, I don't have any product. Now that I have 0 in for both of my products, I'm going to fill in my change. This coefficient here is a 1, so this would just be minus x. This 2 would make this minus 2x. This imaginary 1 would make this plus x. And this imaginary 1 would make this plus x as well. I'm then going to take my values from the problem, remembering that it's important that we convert them to moles first, and then I'll plug them in the table. So 5.75 grams of silicon dioxide and 5.50 grams of sodium hydroxide. I'll set up my conversions to convert these to moles. And I just need to find the molar mass of SiO2 and NaOH. So the mass of silicon is 28.09 plus 2 oxygens would be 32, gives me a mass of 60.09. And sodium is 22.99, oxygen is 16, and hydrogen is 1.01. This gives me a mass of 40 for sodium hydroxide. So to solve the moles of SiO2, I can do 5.75 divided by 60.09 to get 0.0957. And here I can do 5.5 divided by 40 to get 0.1375. So I know these values are now moles, which means I can plug them into the table. So SiO2 is 0.0957 and NaOH is 0.1375. Again, the next step we have to look at is figuring out which one goes to 0. I have less of this, and it only is used up 1x compared to using this at 2x, Because I have less of this, I'm going to just guess that it goes to 0. I can then solve for x. 0.0957 minus x equals 0. X equals 0.0957. I can then plug this in here, 0.0957, to see if this gives me a number less than 0. 0.1375 minus 2 times 0.0957, that gives me negative 0.0539. So I wanted to show you what happens when you pick the wrong one to go to 0. So because I got this as a negative number, that means this is not the limiting reactant. So I need to go back and solve for x again. So instead of making SiO2 my limiting reactant, I'm going to make NaOH the limiting reactant. So when I resolve for x, I would do 0.1375 minus 2x equals 0. 2x equals 0.1375. Divide both sides by 2. And I know that x will be 0.0688. And so now I can plug that in, 0.0688, to get, so 0.0957 minus 0.0688 to get 0.0269. Now, because this is a positive number, I know I picked the correct limiting reactant. So now that I know x, I can go back and plug this in for both products to get 0.0688 moles of Na2SiO3 and 0.0688 moles of water. Again, let's answer these questions now. Limiting reactant is NaOH, because that's what I ran out of. Excess reactant is SiO2. To find the grams of excess reactant, I just take the 0.269 moles of SiO2 that I have left over from my problem, and I convert those to grams. So 1 mole, I can use my molar mass I got earlier of 60.09. And so I can do 0.269 times 60.09 to get 16.16 grams of SiO2 left over. And finally, how many grams of Na2SiO3 are produced? Well, this is the number of moles of Na2SiO3 that are produced. So I can just take this and convert it from moles into grams. So I'll come over here and I'll do 0.0688 moles of Na2SiO3. And I know that in 1 mole, I can find the molar mass. So 2 sodiums, 22.99, plus 1 silicon. Silicon was 28.09, plus 3 oxygens. Each oxygen is 16, so 16 times 3, to give me a molar mass of 122.07 grams. So I can do 0.0688 times the molar mass of 122.07, and I can get that I made 8.398 grams of Na2SiO3, which would be my answer to part C.